All right, in this video we're going to be doing some practice on area between two curves, and this is going to be the extra practice for BC Homework 8.1. So write one integral to represent the area of each region, not two, right? So I couldn't do A in terms of x because that would require two integrals. So for region A, which I'm just going to resketch over here, I'm going to say, all right, this goes over here at here to there. And that's y equals the square root of x minus 1. Okay. Okay, I think the y coordinate up here is the square root of e minus 1, which is kind of a weird number, but we can work with it. Okay, and if we want to write one integral to represent the area of this region, well, then my representative rectangle is going to have to be sideways. Okay, and I'm going to have to integrate with respect to y. Okay, so this length here is right minus left. X equals, well, I need to solve for x. So y squared equals x minus 1, x equals 1 plus y squared. Okay, so on the right, I've got x equals 1 plus y squared. And on the left, I've got, well, this is x equals 0. And I'm going to integrate that as y runs from 0 to the square root of e minus 1. Okay. For b, I'm going to say, all right, this has got, this is something I'm going to just want to do top minus bottom on, right? It's always got the same top and same bottom. So this is y equals the square root of x minus 1, and this is y equals log of x. So my representative piece here is going to be, let's see, y equals the square root of x minus 1 minus y equals log of x. And so we will integrate that as x runs from, where does it start? Starts at 1 and ends at e. You couldn't even see that. Whoops. So, and there should be a dx there. Oh, no, that's very sloppy. That should be a d1. Okay, all right. And then region C, that's 1 to e, that's just log x. All right, so in this one, I feel like you got two options. And so I'll do both of them. On one hand, you could do the vertical representative rectangle. And then that would be top minus bottom, y equals log x minus the x-axis is y equals 0. And so we could integrate that as x runs from 1 to e, definitely. And that's probably the easiest way to go. But if you wanted to go kind of sideways on this one, you could, because you've always got the same right and left. So I'll kind of switch up to blue here and say, okay, on the right, I've got x equals e. And on the left, I've got, well, I need to be able to solve this for x. So if y equals log of x, what is x? How do I get rid? Yeah, it's going to be e to the y because I take e to both sides power. So I'm going to say, well, on the x equals e, and on the left, I have x equals e to the y. Yeah, interesting. And then I can integrate this as y goes from 0 to the square root of e minus 1, for the same reason as before. And I don't know, to me, I don't know. Well, this one I feel like we would actually have a better chance of being able to do by hand because we have an antiderivative for e to the y, and we have an antiderivative for e with respect to y. And that would just be e times y, because e is just a number. This would be troublesome because we don't know how to integrate natural log by hand. Okay, we will eventually, but we don't know that yet. Okay. So that was number 1. Find the exact value of the area of region A. Well, I think I'm going to come back up here, and I'm going to just use scratch paper here and do that. All right, so now I've got integral from 0 to the square root of e minus 1 of 1 plus y squared dy. So I find an antiderivative Oh my. Okay, I'm going to just plug in that square root of e minus 1 plus 1/3 of e minus 1. That's the half power. Take it to the 3. That's the 3/2 power. And, you know, I'm sure we could probably factor out that square root, but like, why would you? Who cares? Minus 0 plus 0. Okay, and that's going to be the exact value of the area of region A. Okay, use a calculator to find the areas of regions B and C. Okay, well, suppose I can do that. So I'm going to integrate from 1 up to E square root of x minus 1 minus natural log of x with respect to x. Let it think. 0.502 or 501. I'm going to show you that these actually give you the same thing. So integral from 0 to the square root of e minus 1 of e minus e to the y, which we're just going to use the letter x on the calculator. It is the same thing. And that's 0.854. But also, if we were to actually integrate this on x, integral from 1 to e of natural log of x dx, we can probably do that too. Log x dx. Hold on, why would that happen? Give me a second. I don't know what it is. That's embarrassing. I think I just mistakenly assumed that this was going to end at that they intersected back at the top, but they obviously don't. Like, there's a gap between the top of region C and the top of the rectangle, and so the height, the top up here, this is y equals the natural log of e, right? So that's y equals e, I think. And so, no, natural log of e is not e, natural log of e is 1. Okay, so I'm integrating from 0 to 1, and then that should probably also give me 1 unit of area. Looks like. So, integral of from 0 to 1. Y equals 0 to y equals 1. X equals e minus x equals e to the y dy. And that's going to be 1. Okay, yeah. Either way. Okay, pardon me. That was rough. The area of region E without a calculator. So, okay. So it looks to me like, all right, so it starts with y equals cosine x, which we know kind of goes like that, and I guess we just need to know the 0 of cosine x is at pi over 2. Right? And then this other curve is 2 minus the cosine of x, and this is region E. Alright, so my representative rectangle is going to be right here. It's going to be vertical. And it'll be top minus bottom. 2 minus cosine x will be 2 minus 2 cosines of x. Alright, so the integral from 0 to pi over 2 of 2 minus 2 cosine x. Okay, antiderivative. is going to be 2x minus 2 sine x, because sine x is a derivative, an antiderivative for cosine x. I'm going to let x run from 0 to pi over 2. And so that's going to be 2 pi over 2 is 2 pi, or no, 1 pi. Minus 2 times the sine of pi over 2. Okay. Y coordinate up there is going to be 1, so 2 times 1 is 2. And then when I plug in 0, I get 2 times 0 minus 2 times the sine of 0. The sine of 0 is going to be 0. And I get pi minus 2. Okay, find the sum of the areas of regions D and F without a calculator. Well, I feel like already knowing region E, now the sum of regions D and F is going to be the area of the rectangle minus E. Okay, I think, and I think that's what I'm going to do. The sum of areas D and F is going to be, well, this whole thing has a width of pi over 2 and a height of 2. Right? Yeah. And so, right? So it's really this minus that. So that's pi minus 2, and that's going to equal 2. Okay? That's the sum of the areas of regions D and F. Number 6. Still this. Region R is bounded by the graph of 1 plus x cosine x and y equals 1. Okay, this is one we're going to have to use a calculator to find the intersections. Actually, we won't. I think, no, I'm not going to need a calculator for that. So, okay, so that's y equals 1, and this is the curve. Okay. So I know that this first intersection is happening at x equals 0, and the second one is going to be where the two things are equal to each other. So where, maybe I'll go down here, where 1 plus x cosine x is equal to 1. And so that's where x times cosine x is equal to 0. And that means if these two things are multiplied together to equal 0, either x is going to equal 0, okay, well that's this one, or cosine x needs to equal 0. And that would be at x equals pi over 2 and 3 pi over 2. Okay, well this is probably going to be 3 pi, or just regular pi over 2. Okay. So I'm going to be integrating top minus bottom. And in this case, top is 1 plus x cosine x equaling y, and the bottom we have y equals 1. So I'm going to integrate top minus bottom, 1 plus x cosine x, and the bottom is 1. And then we're going to let x run from 0 to pi over 2. Okay. Oh, very soon we'll be able to run this integral, but not yet. So this is the integral from 0 to pi over 2 of x cosine x. Okay. You would need integration by parts. You would need a product rule for integrals, and we just don't have that quite yet. So what we do instead is we're going to pull out the calculator. We're going to integrate from 0 to pi divided by 2 on x cosine x with respect to x, and we're going to get 0.571. Okay. All right, now this next one is genuinely challenging. Okay, this is a hard question. So I'm going to try to replicate the region. So it's going to be looks like a downward facing parabola, and then we have a horizontal line. We basically want to move this horizontal line up and down so that this area is equal to that area. We do have an equation for this. This is 2x minus 3x to the third. Oh, so it wasn't a parabola. 2x minus 3x to the third. Okay, and then this is y equals 1. Okay, so y equals c, and it's not going to be 1. So what's going to happen here is that, rather than writing it as two separate integrals that are equal, I'm going to say, well, what would happen is that this is going to be the same as that, but if I just integrated from 0 all the way to the intersection point, which is going to depend on the value of c, you might be noticing, then I should get 0, right? Because first the line's on top and then the curve's on top, and if they're the same, then it would go backwards, and in total I'd have a 0 integral. So that's going to be kind of my first stop, is I'm going to say, all right, the integral from 0 to k of, it doesn't matter. You can do top minus bottom or bottom minus top, because it's going to equal 0, right? So I'm going to say 2x minus 3x to the third minus c. With respect to x. And let's see, what am I going to do here? I think I'm going to actually anti-differentiate and run this and get it kind of in terms of k and c, and then kind of look at some sort of relationship between k and c. Okay. So I'm going to anti-differentiate. So that's x squared minus 3/4 x to the fourth minus cx, as x runs from 0 up to k. And that needs to equal 0, right? That was the whole idea. So, and then I'm going to plug in k. So I'll have k squared minus 3/4 of k to the 4 minus k times c, or c times k, and whatever. Okay, minus whatever I get when I plug in 0 for x, but when I plug in 0 for x, those are all going to go 0, so I'm just going to leave it like that. Okay. Now, let's see, how do I want to say this? So I'm just going to kind of focus on this point right here. So this is the point that is, it's got x coordinate k and y coordinate c, right? But also I know that if I plug in k for x, well, that's going to have to equal c because they have that same point. So I'm going to say that 2k minus 3k to the 3, that's equal to c, right there. Okay. And so then I'm going to substitute on c, and then I'll have a polynomial entirely in terms of k, and then I'm just going to hope for the best. Okay. I think that this one, if I recall correctly, is one that it works out. Okay. Even though it's 4th degree, I'm a little concerned about this 4th degree aspect, but what can I do? Can't really do much. So I'm going to substitute on c right there. So k times c is 2k minus 3k to the 3. And now we're kind of off to the algebra races. So okay. 12/4 minus 3/4 is 9/4. K to the 4 minus k to the 2. Okay. Wait a second. I'm not sure why I was tripping on the fact that I can factor out this k squared, and I'll be left with 9/4 k squared minus 1. And, well, that k squared, that tells me that k could equal 0 and make this equation true. But if you think about it all the way up here, okay, yeah, if we move c all the way down to the x-axis, yeah, there is no area over there to be equal to, so that's not going to make any sense. So what I'm going to say is that 9/4 k squared minus 1 is equal to 0. That means that, well, basically 9k squared equals 4. And that means that k squared equals 4/9, or k is equal to positive or negative 2/3, but I know it's positive based on the drawing. So I've got that. And now I think I'm pretty much ready to find the value of c, right? That was find the value of c that makes the two shaded regions equal in area. So c is 2k minus 3k to the 3. So c is 2k is 4/3 minus 3 times 8 over 27. Okay, well, I've gone this far. I can do the rest. So 4/3, I'm going to need to go to 9ths because of I'm going to simplify that as 8 over 9. So 4 is going to be 12/9 minus 8/9 is equal to 4/9. And that's the value of c that makes the two areas equal. That was a good problem. But not something that you're going to have to do again in AP Calculus or anything like that. That was just a special extra practice problem for you. And let's see, I've got a couple more problems. Yeah, here's the extra sheet. Find the area of u using an integral on x. Oh, okay, so we're going to find u and v with both x and y. Okay, well, I can do that. All right, I'm going to start with u. So I'm going to go a little out of order here. So u is x to the 4 plus 1. All right. So on one hand, I can do it in x. And for my red pen, here it is. In x, I'm going to say top minus bottom. I'm going to be integrating a top is y2 minus bottom is x to the 4 plus 1 dx. And that's as x runs from 0 to 1. You can see it on the figure. And that will be 2 minus 1 is 1, so it's integral from 0 to 1 of 1 minus x to the 4. And I'm going to do that real quick. So 1 minus a fifth is 4/5. Plug in 0, that's all I got. Okay, it's 4/5. Cool. Okay, I can also do this in y. And then my representative rectangle will sit sideways. And okay, if this is y equals x to the 4 plus 1, I'm going to need to solve for x. Okay, so I'm going to just do that right now. So y minus 1 equals x to the 4. X equals really positive or negative 4th root of y minus 1. I know it's the positive 4th root because I'm over here where x is positive. Okay. So now I'm going to be integrating right minus left. On the right, I have the curve, 4th root of y minus 1. On the left, I've got x equals 0. Yeah, x equals 4th root of y minus 1 minus x equals 0. And that's as y runs from 1 to 2. Okay. You can see it goes from 1 to 2 in the image. You could kind of investigate a little more. Y is going to range from 1 to 2. So this is the, integral from 1 to 4, give myself a little more room, of y minus 1 to the 1/4 power. So 4/5 of y minus 1 to the 5/4 as y runs from 1 to 2. I don't know what happened there. Right, so 2 minus 1 to the 5/4 is going to be, well, 1 to the 5/4. It's going to be 4/5 times 1 minus 4/5 times 0. And, well, that's going to be 4/5 again, which is kind of what we'd hoped to show. It's the same area, regardless of how we computed it. Right, then there's going to be region V, which is going to be pretty similar. It's just the one that's underneath x to the 4 plus 1. Oh, goodness. That was not the best one ever, but it'll be fine. Yeah, that'll be better. All right, so if I want to integrate an x, I'm going to be doing top minus bottom, and that will be the integral of y equals x to the 4 minus 1 on top minus y equals 1 on the bottom. We're going to integrate with respect to x as x runs from 0 to 1. And so this will be the integral from 0 to 1 of x to the 4 minus 2, and that's 1/5 x to the 5th minus 2x as x runs from 0 to 1. X to the 4 plus 1. Okay, I was going to say this is going to come back negative, and that wasn't going to make any sense at all. Okay, x to the 4 plus 1 minus 1 is, yeah, that's just going to be x to the 4. Whoops. Good now. And so that's going to be equal to 1/5 minus 0, which actually makes sense, right? If you can see that was a square that had area 1, and this was 4/5, this should probably be 1/5. And y, let's do this one. Let's say this is, well, I already did x equals the 4th root of y minus 1. And that's going to be on the left. So when I do right minus left, it's going to be x equals 1 minus x equals y minus 1 to the 1/4 power. I might start with that. And I'm going to integrate as y runs from 1 to 2 again. This is y equals 1, and this is, well, that's 0.12. All right. And we're integrating this with respect to y. So this will be, 1y. Minus 4/5 y minus 1 to the 5/4 as y runs from 1 to 2. Okay. So this is going to be 2 minus 4/5 minus 1 minus 0. And so in total, I've got 2 minus 1 is 1 minus the 4/5 is going to equal 1/5. So regardless, I'm showing that area is 1/5. And that's all for the extra practice for area between two curves. Thanks for watching.